So the title of this video is More Laws, or simply laws I forgot to put into the previous video. And they're really just expansions on the ones we talked about before. Namely, let's start with the ideal gas law. PV equals nRT. P is pressure, V is volume, N is the number of moles, R is the gas constant, 0.0821 liter atmospheres per Kelvin mole, and temperature is, or T is temperature in Kelvin. The number of moles of something can be found by taking its mass, that's a little bit better, taking its mass and dividing it by its molar mass. That's how you find the number of moles if you were dealing with grams of something. So we really, if we were given the grams of a gas, we could rearrange this formula and plug in mass divided by molar mass for N, which gives us this crazy looking formula. But with this, we are able to find the molar mass of a gas if we know its mass and its volume and its pressure and its temperature, or mass and volume are related through density. So if we know the density of a gas, if we rearrange this formula a little bit, there's one rearrangement, there's the next, take the reciprocal, and M divided by V, that's volume. I mean density. So molar mass of a gas equals its density times 0.0821 times its temperature in Kelvin divided by pressure. Some people remember this as the dirty cat, or the molar mass kitty cat, because all good cats cover their pee in dirt. Personally, I remember it as the camping formula. Whenever you go camping, you cover your pee and other issues in dirt so that bears don't come and eat you. That's probably not necessarily true, but that's personally how I remembered it. I cover my pee with dirt. Another note on density is that while liquids and solids report their densities in grams per milliliter or grams per cubic centimeter, gases report densities in grams per liter. Because in order for this formula to work out, this density would have to be in grams per liter to cancel out the liters in your R value. And if you're at STP and dealing with 1 mole of any gas, you can find its density by dividing by 22.4. So some multiple choice questions will ask you about different gases and whether they sink or float in air. So air is approximately 80% nitrogen, approximately 20% oxygen. And I know there are other trace amounts, but we're approximating, thus the squiggly line. I see you, squiggly line. So nitrogen, I have 2 nitrogen atoms, each atom's 14, so 2 times 14 is, I have a molar mass of 28. Oxygen is 16, 2 oxygen atoms, 2 times 16 is 28. 32, sorry. So the weight, the average atomic mass, or the atomic mass of air, we can say it comes out to be 28.8. So a molar mass of air, 28.8. Which means at standard temperature and pressure, if we take 28.8 divide by 22.4, comes out to be 1.3. So gases whose molar masses are greater than 29 will sink at standard temperature and pressure, and gases whose molar mass are less than 29.9 will float. Another law that I neglected to go into is Dalton's law, or Dalton's law of partial pressure, which simply states that if I have 2 gases, each gas exhibits its own partial pressure based upon the number of moles present, and if they are combined, that system is going to have a new pressure that is the total of those 2 pressures. So I have 2 gases. If they are mixed together into the same container, the total pressure of that system is the sum of their partial pressures. And you don't have to have 2 gases. You could have infinite number of gases, but each of their partial pressures added together would be the total pressure of that system. You can determine the partial pressure of any particular gas in a system by taking the total system's pressure and multiplying it by the mole fraction of that particular gas. So assuming each one of these dots represented a mole, the mole fraction here would be 4 divided by 14, because that's the total number of moles of gas in this system. Lastly, gases are typically captured via water displacement, meaning as a reaction occurs, if a gas evolves out of it, it's typically captured via water displacement, meaning as it comes out, travels up the tube because heat source is down here, it's going to try to disperse itself, moves down the tube, and is deposited in some capture instrument, a flask, a graduated cylinder. As more gas is captured, it displaces the water. However, because there's water here, water exhibits a vapor pressure, because water molecules are becoming water vapor, an equal rate at which water vapor is becoming water molecules. There exists a phase equilibrium here. So you need to take out of the equation this water vapor, this vapor pressure from water. And to do that, you would need to look up the vapor pressure of water at whatever temperature this gas was collected. That will return for you a pressure. Subtract the pressure in the container. Subtract from the pressure in the container the vapor pressure of water at that particular temperature to find the pressure of that gas that was evolved.